Good morning. Let's start today's session. So today we are going to study what is pointing theorem and pointing vector, right? So we have studied in the previous class that if this is the electric field and if this is the magnetic field, then this is the direction of propagation of electromagnetic wave. And according to the theory studies we have done, you know what is a cross product, right? So what is A cross B? We have A cross B is equal to AB into sine theta into a unit vector A, right? N, right? So if A is in the X direction and B is in the Y direction, then this resultant vector will be in the Z direction. Similarly, here also, if E is the electric field in say y direction, if m is in the x direction, then this will be in the z direction. So the propagation of power or the wave occurs in the z direction. So this concept is what we are going to use over here. So we will explain the Poynting theorem such that assume a volume, say this volume, and the power is emanating or generating from this volume. So while doing that, there will be ohmic laws inside it. So Poynting theorem states that the net power flow out of a given volume V is equal to the time rate of decrease in the energy stored with V minus the ohmic laws. So this is the equation. P is equal to E cross H. This P is known as pointing vector. I'll call it as pointing vector. Why? Because it is pointing towards another direction. That is why it is known as pointing vector. Pointing. Instead of I, we are using the word P O Y. Pointing vector. Clear? So it is nothing but E cross H. Why? Because the power is moving in the third direction of that of E and H. E H stands for magnetic field, no? So this is the waveform representation. See, this is how this blue line indicates the electric field. See, somehow over here a particle is being maximally accelerated, and as a consequence this wave is getting propagated. So here the particles are getting accelerated. So each and every point the particles are there, they are moving in this way and this way. So this is electric field. This blue line indicates electric field in this direction. This red indicates the magnetic field in this direction. So see, these two things are 90-degree apart, 90-degree phase shift between. So three-dimensionally they are 90-degree, and the wave is moving the z direction, third direction. Okay, so let's see the derivation, right? So we have to study it in a step-by-step manner. So let's start with step one, right? So in each step we are going to make slight changes and rearrange the equation, and we are going to derive the Poynting vector P. So Poynting vector P equal to E cross H. So keep in mind that we are going to derive this term P equal to E cross H. So we have to get E cross H somehow. So combining that, we have one equation, that is Maxwell's equation for using Ampere's law. So we know Ampere's law, right? So what is Ampere's law? Del cross H is equal to J, no? But there is a modification of Ampere's law occurs. What is it? We have included displacement current. So this is a modified Ampere's law, that is del cross H is equal to J plus JD. JD is nothing but displacement current density, and JD is dou D divided by dou T. See, in this equation you have D. Also D, you know that epsilon E, right? So E is there now. Then over here we have H. So we have H and E over here, right? So in the form of D. So we have E and H combination. So this is the apt equation for deriving the Poynting vector P. So first thing is we have to take Ampere's law in the modified form. Then take out J. So del cross H minus dou D by dou T will be equal to J, this equation. This will be our step 2. Step 2 is we have to take the dot product on both sides. So we have to take this E dot J over here, E dot over here, E dot over here. So E dot J equal to E dot del cross H minus E dot dou D divided by dou T. So from this term, we are going to get somehow E cross H. We'll see using some identity. So del dot A cross B, this an identity, del dot A cross B is equal to B. This term B minus del cross A minus, instead of B you use A dot del cross B. This is the equation. So that is going to be a step 3. See, this is our step 3. Study it in step manner, otherwise you won't remember it. So this is the equation I am rewriting, identity. Then instead of A I am replacing it by E, instead of B I replace it by H. So del dot E cross H is equal to H dot E cross del cross E minus E dot del cross H. So in the previous equation we have E dot del cross H. So which is E dot del cross H, we kept it on the left side, we keep all the other terms on the right side. So we have H dot del cross E minus del dot E cross H, right? So what we did was replace that E dot del cross H by this equation. So we'll get H dot del cross E minus del dot E cross H. Just substitute this over here, minus E dot dou D by dou T, which is there in the earlier equation, right? Also, we know we have to substitute certain things which we know. What is del cross E? According to Faraday's law, we know that del cross E is equal to minus dou B by dou T, where B equal to mu H and D equal to epsilon E. So B you have to use here. So B substitute it over here. So mu, take it outside, minus mu dou H by dou T, right? So this substitution you have to give it over here, del cross E, and also put D equal to epsilon E. Why? Because we need E and H at the end. So E dot J equal to H dot minus mu dou H by dou T minus del dot E cross H minus E dot dou by dou T into epsilon E, right? So epsilon, take it outside. So this is the equation we have reached. Now what I'm doing is take the minus outside. So minus mu, take it outside, minus mu H dot dou H by dou T minus epsilon E dou E, put it this inside over here, minus del dot E cross H. Why? Because at the end we should get E cross H. So keep E cross H on one side, and this is somewhat similar to this. This is magnetic field, this is related to electric field. So combine this is magnetic field and this is electric field. So we're just combining those similar looking terms over here, and we rewritten the equation. So step 3 is nothing but we started with an identity del dot like that and substitute in the previous equation. Then we have used Maxwell's second equation and substituted certain terms over there after using the identity. Then we rearranged the term and we got an equation like this. Keep it like that. Next, this is our step 3. This is our step 4, right? So we are talking about step 4. Step 4, we have the earlier equation have written once again. I'm going to use a small mathematical step, that is, we know what is 1 by 2 into d by dt of x square. How will you write? X square, if you differentiate this with t, we'll write 2x, right? So 1 by 2 into 2x into dx by dt you can write. So 2 and 2 get cancels. So x into dx by dt. So half d by dt of x square is equal to x into dx by dt. Just look here, this term and this term looks like x into dx by dt now, x into dx by dt. So how can we rewrite it? Using 1 by 2 dh square by dt, right? So see, E dot j is equal to minus, we keep it outside, this term outside, this term is also intact. So this term we have replaced. So h into dou h by dou t, we replace it by 1 by 2 dou by dou t of h square. Over here epsilon take it outside, the rest of the term is E dou E by dou T, replace it by 1 by 2 dou E square by dou T minus del dot E cross H, right? So we just taken the half inside, C minus or outside. So this is E dot J. E dot J equal to minus, take it outside itself, dou by dou T, 2 put it inside. So 1 by 2 mu h square you have. So there is no thing. It's not squared. Okay. So dou by, there is nothing like that. So epsilon half epsilon E square minus E cross H we have. Okay. That is step 4. So what we did in the step 4, we have the equation, we just use this mathematical identity, that is half dx square by dt is equal to x dx by dt. We just substituted it into these two terms, we just combined it together and keep it such. Next is we have reached on to step 5. Step 5, we rewritten the equation once again, such that dou by dou t is outside, and we have just written the equation like this. Now what we are doing is apply a volume integral on both sides. In step 5 what we are doing is we are just applying a volume integral on both sides. See, so I have tried volume integral of E dot J into dv minus, take it outside, so volume integral dou by dou t of the first term into dv minus volume integral of del dot E cross H into dv you have to write. Now at the end we should get pointing vector v, so this is nothing but E cross H. So I am taking this term to the left hand side, so volume integral of del dot E cross H is equal to minus volume integral of dou by dou t mu s square plus epsilon e square into dv. Put this term over here, so minus volume integral E dot J dv, that is step 5. So in step 5 what we did is just rearrange a whole thing and put a volume integral, that's it. Now step 6, we are reaching on to the final stage. This is the final step. So see over here, this term you have now, so we can apply divergence theorem over to that. What is divergence theorem? Surface integral of d dot ds equal to volume integral of del dot d dv. So I can write this as, this is del dot, like that, volume integral of del dot d, instead of d we have E cross H. So this equivalency is surface integral of E cross H ds, isn't it so? See, volume is converted into surface. Volume is converted into surface using this particular identity. This is divergence theorem we have studied in module 1. So volume integral del dot E cross H is converted into surface integral E cross H ds. So instead of this del dot E cross H, we can write surface integral of E cross H ds equal to minus of volume integral dou by dou t of 1 by 2 mu square plus 1 by 2 epsilon e square dv minus E dot J, volume integral of E dot J into dv. This is a final equation. See, this is the part 1. This is part 2 and this is part 3. We will see how it works. So part 1 represents, see, this is a volume. This is a volume we are considering, assuming. So in that volume there is some kind of energy. The power is there. So we are inserting power, P in is there. Then if you are inserting power into this volume, some energy is stored as electric field E. Then some energy is stored as magnetic field B, and some energy is lost in the form of ohmic. These are stored energy, this is loss, ohmic energy, and the power comes out. So how can we write? So power in is equal to power out minus losses. See, this is power out. This part 1 is power out. This is power inside, power stored energy. It is nothing but combination of electric field and magnetic field. And third one is the power loss, right? So this is how the pointing theorem is explained. See, the pointing vector P is equal to E cross H. It is normal to both E and H, and therefore it's along the direction of propagation of wave. So the AK, if AE is the unit vector along E and AH is the unit vector along H, then AE cross AH will be AK, will be the unit vector along the propagation. So it is P points along the AK direction. See, this is the AK direction we are saying. So this is known as pointing vector. So that's all about pointing.